Hello everyone. I want to take a minute to review the lab that was about torque, and this was the introduction to torque. Now, torque is the angular analog to force. When I say that, I mean torque is the angular equivalent of force. Remember, in a straight line, if we push something, we expect it to accelerate. That means speed up, slow down, or change direction. And that force causes some acceleration. We have net force equals mass times acceleration. The angular equivalent to that is torque, which means instead of something moving along a straight line, if I have a disk that's free to rotate around some point, then when we push on it like this, it starts to spin, it starts to rotate. And this is called torque. So torque is a force's ability to cause rotation. And it depends on more than just how big the force is. Torque depends on both force and lever arm. Lever arm is a distance, and what you guys saw in lab was it mattered how far away you were from this axis of rotation. If we had something over here and we wanted to balance it with a force over here, we could use a big force really close, or we could use a small force further away. And we're going to talk a little bit more about that in a minute, but lever arm is that perpendicular distance between the applied force and the axis of rotation. It is also important to notice that torque is a vector. Okay? If I have a force over here, it's trying to cause this thing to rotate this way, which is clockwise. If I have a torque over here, a force over here, it's trying to make it rotate back around this way, which is counterclockwise. Those are Wow, that was way too many C's. Counterclockwise. Those are opposite directions, so torque can be positive or negative. We generally think of counterclockwise as positive and clockwise as negative, but you can usually choose your reference frame to make the math easier. So whatever you want to do there. Now, what I said earlier was lever arm matters, and it's a perpendicular distance. First we'll look at the perpendicular case, then we'll look at a case where the angle is goofy. So first, if I have something that's hanging over here, and I don't know, say I've got 10 newtons of force pulling down over here, and I want to balance that with the force over here, and say this is 5, 10, 15, 20 centimeters. How much force do I need to apply if I'm only going to apply the force right here at 10 centimeters? Well, this force causes a torque, and the torque that it causes is equal to force times lever arm. We give the symbol for lever arm as R because if this thing were actually to rotate freely, it would carve out a circle with a radius R. So R is a lever arm. Now, that means this force would be 10 times 0.2, which is, right, 0.2 is my lever arm in meters, which is 0.2 Newton meters. Now, a Newton meter in torque is not the same thing as a Newton meter for work. Remember, work is equal to force times distance times the cosine of the angle between them. This is a scalar quantity. This could have been positive or negative because of the cosine, but that just told me are we gaining energy or losing energy, not which way the force was actually going. So this was a scalar quantity. It does not include direction, and it's measured in joules. Torque is a vector quantity. It is not measured in joules, it's measured in Newton meters. Now, back to the question, how much force do I need to apply over here to balance this? Since I want to have an equal but opposite torque, I want my torque over here to also be 0.2 Newton meters. Since the direction of the force is going to be down, we've already taken care of the direction. So that means my force times my lever arm is 0.2. Since my lever arm is only 510 centimeters, I have F times 0.1 meters equals 0.2, and I can divide both sides and I get a force of 20 newtons. So just like we expected, since we've got half as much lever arm over here, we need twice as much force for the torques to balance. Hopefully this is just a verification of what you saw in lab. Now the last thing I want to take a look at is what happens if that axis of rotation, or the lever arm, I'm sorry, and the force are not perpendicular to each other. So here's my axis of rotation, and here's a lever arm. And let's say my force, instead of coming in at a perpendicular angle, comes in at some other angle. So I have, say, a 45-degree angle between my lever arm. Well, instead of even calling that an angle, I'm just going to call it theta. So I have some angle between my lever arm and my applied force. What's the effect on this? Well, to make this thing cause the most torque, we would want this force to be exactly perpendicular because then it's all trying to cause rotation. But if you look at this, some of this force is actually acting this way. That doesn't cause any rotation at all. Some of this force is acting this way. That part does cause rotation. Since this is the angle theta, this up here would also be the angle theta. This is the force F, this is the lever arm R. Then I could say that the torque is caused by the perpendicular component of force, which would be F times the sine of theta times R. But this means I had to redraw my triangle like this, and I'm paying attention. Now it does work, and it's okay with that, but the traditional method of doing this is actually to take and extend your force vector back so that you can draw a perpendicular axis of rotation from your lever arm, or a perpendicular lever arm from your axis of rotation. So if I extend my force back, then I'm going to go ahead and draw my lever arm from my axis of rotation until it's perpendicular to that force, which looks to be about there. Then what I can say is this is a right angle between my force and my lever arm. This is the angle theta. This is the hypotenuse R, which makes this side R sine theta. The force is now still applied in its original direction, and it's perpendicular. So I get torque is equal to Fr sine theta. And this is usually how we derive it. Not a big deal. I don't care which way you choose to do it. You're still essentially finding the component of the vector that has the force and the lever arm perpendicular to each other.